The intellectual landscape of fundamental physics in the early 1960s presented a panorama of bewildering complexity. The uncertainty world of protons, neutrons, and electrons had been shattered by discoveries from particle accelerators, revealing a veritable zoological garden of new particles. This proliferation, primarily of hadrons, which are particles that feel the strong nuclear force, created a crisis of understanding. Physicists faced a disorienting collection of interdisciplines, kaons, lambda particles, sigma and Pi 11 baryons, each with its own mass, charge, and esoteric quantum numbers like strangeness. The situation was reminiscent of the state of chemistry before the periodic table. There was an abundance of data, with a conspicuous absence of an underlying organizational principle. A profound theoretical breakthrough was needed to transmute this chaotic catalogue into a coherent and predictive science. The first major step toward this new order was the advent of a classification scheme known as the Eightfold Way, independently proposed by Murray Gell-Mann and Yuval Neeman in 1961. This elegant framework employed the mathematics of the special unitary group of degree 3, or SU3, to group hadrons into families, or multiplets, based on their shared symmetries. Baryons, the heavier hadrons like protons and neutrons, fit neatly into octets and decuplets, their positions within these geometric patterns determined by their isospin and strangeness. Mesons, the lighter hadrons, formed similar groupings. The Eightfold Way achieved remarkable success, its most celebrated triumph being the prediction of a hitherto unseen particle, the omega-baryon, which was required to complete a baryon decuplet. Its discovery at Brookhaven National Laboratory in early 1964 provided stunning validation for the SU3 symmetry scheme. Yet, for all its predictive power, the Eightfold Way was fundamentally a taxonomy. It described the patterns but offered no explanation for their origin. It was a periodic table without an atomic theory, a map of the world without a theory of plate tectonics. The central, unanswered question remained: what physical reality underpinned these beautiful mathematical groupings? The answer, when it arrived in 1964, was more radical and conceptually challenging than most of the physics community was prepared to accept. It was in this context of established pattern and absent foundation that two physicists, working independently, formulated a revolutionary hypothesis. At the California Institute of Technology, Murray Gell-Mann, a principal architect of the Eightfold Way, penned a brief, almost tentative paper titled A Schematic Model of Baryons and Mesons. In a display of his characteristic intellectual flair and literary erudition, he christened the hypothetical constituents of his model quarks, a whimsical term plucked from a line in James Joyce's Finnegan's Wake 3 Quarks for Muster Mark. Gell-Mann proposed that all known hadrons were composite systems built from a small set of more fundamental entities. He posited three types, or flavors, of these quarks: the up quark, the down quark, and the strange quark, so named because its presence accounted for the mysterious quantum number of strangeness. These were envisioned as spin 1/2 fermions, but they possessed a truly startling and unprecedented property: fractional electric charge. The up quark was assigned a charge of positive 2/3 of the elementary charge, while the down and strange quarks both carried a charge of negative 1/3. This feature was profoundly counterintuitive, as every particle ever observed had possessed an integer multiple of the electron's charge. Gell-Mann's model stipulated simple construction rules. Mesons, like the pilon, were composed of one quark and one antiquark. Baryons, like the proton and neutron, were built from three quarks. A proton, with its charge of positive 1, was a composite of two up quarks and one down quark, yielding a total charge of 2/3 plus 2/3 minus 1/3, which equals 1. A neutron, with its zero charge, was composed of one up quark and two down quarks, a sum of 2/3 minus 1/3 minus 1/3, resulting in 0. The model elegantly reproduced all the known hadron multiplets of the Eightfold Way. The octets and decuplets emerged naturally from the combination rules of the three fundamental quarks, dictated by the mathematics of SU3. Despite the model's explanatory power, Gell-Mann himself remained circumspect, presenting the quarks more as convenient mathematical fictions or bookkeeping devices than as actual, physical particles. The notion of fractional charges and the apparent impossibility of isolating a quark made the idea of their physical existence seem remote, a useful abstraction for understanding symmetry, but perhaps little more. Concurrently, and in complete isolation from Gell-Mann, a young postdoctoral researcher at CERN named George Zweig was developing an almost identical idea from a different conceptual standpoint. Zweig, in a more detailed and less guarded internal report, an SU3 model for strong interaction symmetry and its breaking, proposed what he called ACEs, like Gell-Mann's quarks, Zweig's aces came in three varieties with the same fractional charges and spin assignments. His motivation, however, was rooted less in pure symmetry classification and more in understanding the dynamics of particle interactions. Zweig was particularly puzzled by certain decay patterns, for example the observation that the phi meson decays into two kaons but almost never into a rho meson and a pion, a process that should have been energetically favourable. He developed a graphical rule, now known as the Zweig rule or ZI rule, which stated that diagrams with disconnected quark lines were suppressed if the phi meson was composed of a strange quark and a strange antiquark, its decay into kaons, which also contain strange quarks, with a simple rearrangement. Its decay into pions and rho mesons, which contain only up and down quarks, would require the complete annihilation of the initial strange quark pair and the creation of a new up or down pair, a disconnected and therefore suppressed process. This provided a dynamical justification for the model. Zweig's conception of his aces was emphatically physical. He viewed them as real, concrete, fundamental constituents of matter, akin to the way protons and neutrons constitute atomic nuclei. This conviction placed him at odds with the prevailing theoretical climate. His CERN report was met with skepticism and even derision from the senior theoretical establishment. It was deemed too radical, too speculative, and the idea of postulating unobserved, fractionally charged particles was considered poor form. The paper was effectively blocked from publication in a mainstream journal, circulating for years as a preprint, a piece of underground literature for the initiated. The parallel emergence of this profound idea from two minds, one a celebrated leader in the field and the other a junior researcher, approaching from distinct intellectual angles, underscores the ripeness of the problem. Gell-Mann's caution and abstract framing allowed the idea to enter the discourse with a veneer of academic respectability, while Zweig's concrete, physical insistence, though initially suppressed, foreshadowed the direction in which the field would ultimately be driven by experimental evidence. The quark hypothesis, in both its guises, provided a beautiful and economical explanation for the eightfold way, but in the mid-1960s, it remained an unproven and highly speculative proposition. The crucial question was whether quarks were mere mathematical artifacts or tangible components of reality. The first major piece of evidence to shift the consensus came with the discovery of the omega- particle. While its existence was predicted by the SU3 symmetry of the eightfold way, the quark model gave it a specific and concrete internal structure, a baryon composed of three strange quarks. The confirmation of its existence with the predicted properties lent immense credibility to the entire theoretical edifice upon which the quark idea was built. However, the definitive evidence that transformed quarks from a clever scheme into physical objects emerged from a series of landmark experiments conducted at the Stanford Linear Accelerator Center, or SLAC, in the late 1960s and early 1970s. A team led by Jerome Friedman, Henry Kendall, and Richard Taylor performed what became known as deep inelastic scattering experiments. The methodology was a modern-day version of Ernest Rutherford's gold foil experiment. Instead of alpha particles, the SLAC experimenters fired a beam of high-energy electrons at stationary proton and neutron targets. If the proton were a diffuse, uniform sphere of charge, the electrons would be expected to pass through with only minor deflections. The results were starkly different. A significant number of electrons were scattered at large angles, as if they had collided with hard, point-like objects inside the proton. This scattering pattern was precisely what one would expect if the proton's charge were concentrated in small, dense, quasi-free constituents. Richard Feynman, analysing these results, had developed a theoretical framework describing such constituents, which he called partons, a deliberately generic name for the parts of the proton. It soon became clear that the properties of these experimentally revealed partons matched the theoretically postulated properties of quarks perfectly. The SLAC experiments provided the smoking gun, the direct visual evidence, albeit indirect, that protons and neutrons were indeed composite particles. The point-like scattering centers within them were Gell-Mann's quarks and Zweig's aces. The era of quarks as mere mathematical constructs was over. They had been promoted to the status of physically real inhabitants of the subatomic world. The confirmation of the quark's physical existence resolved one great mystery, while simultaneously creating a new, profound paradox. The omega- particle, now understood to be composed of three strange quarks, presented a direct challenge to one of the most fundamental tenets of quantum mechanics, the Pauli exclusion principle. This principle states that two identical fermions, particles with half-integer spin-like quarks, cannot occupy the same quantum state. Yet, in its ground state, the omega- appeared to consist of three identical strange quarks with their spins aligned in the same direction, a flagrantly forbidden configuration. The solution to this conundrum was as bold as the quark hypothesis itself. In 1964, Oskar Greenberg, and later more formally by William Bardeen, Harold Fritsch, and Gell-Mann, proposed the existence of an entire new type of charge, which was whimsically named color. This property had nothing to do with the visible spectrum of light. It was a new, hidden quantum number. The theory proposed that each flavor of quark up, down, strange, and any others yet to be discovered could exist in one of three color states, designated as red, green, and blue. Antiquarks carried corresponding anticolors anti-red, anti-green, and anti-blue. The Pauli exclusion principle was rescued by postulating that the three strange quarks in the omega- each possessed a different color, making them distinguishable after all. This new idea came with a powerful new constraint: all observable particles, all hadrons, must be color neutral or white. A baryon, composed of three quarks, achieves color neutrality by containing one red, one green, and one blue quark, whose colors combine to be white. In analogy to additive color mixing, a meson, composed of a quark and an antiquark, is color neutral because it contains, for example, a red quark and an anti-red antiquark, which cancel each other's color charge. This hypothesis brilliantly solved the spin statistics problem and also provided a natural explanation for a glaring empirical fact: the non-observation of any particles other than those with quark-antiquark or three-quark combinations. Particles like a two-quark state or a four-quark state would be unable to form a color-neutral combination and therefore, according to the theory, could exist. What began as a solution to a statistical puzzle rapidly evolved into the foundation for a complete dynamical theory of the strong nuclear force. The symmetry of color charge, described by its own special unitary group of degree is time and S-unity of color, gave rise to a theory known as quantum cryptodynamics, or QCD. In the framework of QCD, the strong force that binds quarks together inside hadrons is mediated by the exchange of massless, spin-on particles called gluons, in analogy to how a photon mediates the electromagnetic force between electrically charged particles. Gluons mediate the strong force between color-charged particles. There are 8 types of gluons, and they themselves carry color charge, a crucial feature that distinguishes QCD from the theory of electromagnetism and leads to its most remarkable properties. The dynamics of QCD explained the two most salient and seemingly contradictory features of quark behavior. The first is asymptotic freedom, the phenomenon that at very high energies and short distances, such as those probed in the SLAC deep inelastic scattering experiments, the force between quarks becomes very weak. They behave almost as free particles, which is precisely what the experiments had shown. The second, complementary property is confinement. At lower energies and larger distances, on the scale of the size of a proton, the force between quarks becomes immensely strong. The energy required to separate two quarks increases with distance, so much so that it is impossible to pull a single quark out of a hadron. Attempting to do so provides so much energy to the system that it becomes more favorable to create a new quark-antiquark pair from the vacuum, resulting in two new hadrons instead of an isolated quark. Confinement provides the ultimate explanation for why free quarks are never observed in nature. They are perpetually imprisoned within their color-neutral hadrons. This theoretical edifice, crowned by the development of QCD, marked the complete triumph of the quark model, transforming it from a schematic suggestion into a cornerstone of the standard model of particle physics. The 1964 proposals of Murray Gell-Mann and George Zweig represent a watershed moment in the history of science, a paradigm shift in our conception of matter's ultimate structure. Their work initiated a journey that took the quark from a whimsical, Joycean neologism and a controversial, suppressed manuscript to the central protagonist in our modern story of the strong interaction. The initial resistance, rooted in the seemingly absurd notion of fractional charges and the failure to detect isolated quarks, gradually yielded to the overwhelming weight of experimental evidence and theoretical coherence. The discovery of the omega- baryon validated the underlying symmetry, while the deep inelastic scattering experiments at SLAC provided the direct proof of their physical reality as the hard, point-like partons within protons and neutrons. The subsequent introduction of color charge not only resolved the spin statistics crisis but also paved the way for quantum cryptodynamics, a rich and predictive theory that beautifully accounts for both the quasi-free behavior of quarks at high energies and their permanent confinement within hadrons. The quark model's success continued with a prediction in subsequent discovery of three heavier quark shell in 1974, bottom in 1977, and top in 1995, completing the three generations of matter in the standard model. The twin insights of 1964, born of a need to impose order on a chaotic particle zoo, ultimately redefined the very meaning of elementary. The proton and neutron, once considered fundamental, were revealed to be complex composite systems. The true elementarity was found one level deeper, in the fractionally charged, color-bearing, and permanently confined quarks. This intellectual odyssey from pattern recognition to physical reality stands as a testament to the semiotic relationship between theoretical speculation, mathematical symmetry, and decisive experimentation, a process that continues to guide our quest to understand the fundamental architecture of the universe.